a steam radiator building, right? When people in steam radiator buildings think it's too hot in the wintertime, they don't call down to the boiler room and have them turn their service down. They just open a window.
Hi, everyone. My name is Tom Raftery. Welcome to the Climate Confident podcast. With me on the show today, I have my special guest, Drew. Drew, welcome to the podcast. Would you like to introduce yourself?
Sure, Tom. Thank you for having me today. My name is Drew Maggio. I'm from Long Island, New York, and I'm the technical director of Highmark Building Efficiency. Highmark represents manufacturers from around the world to provide buildings in New York City with the best technologies for electrification, decarbonization, and sustainability.
And for people who don't live and breathe HVAC, how did you get pulled into this space in the first place?
Yep. So I started originally as a mechanical engineering student at Stevens Institute of Technology in Hoboken, New Jersey. I ended up securing an internship with Highmark over the summer before my junior year. And during that internship, one of the big things we looked at was air source heat pumps and how they would freeze over in the winter. For electrification of buildings to get them off of boilers and fossil fuels in the winter and move them over to heat pumps so that they can electrify, that has really been the biggest concern. Do these things work at low ambient air temperatures? And somebody cracked the joke, we should put them in the subway tunnels because it's always too hot down there. That blossomed into a capstone project for me to work on my senior year. It was sponsored by Highmark Building Efficiency. So we got to work hand in hand with a real engineering firm, the MTA, looking at different buildings. And at the end of all that, I said, I want to keep on working on this. I want to keep on pushing the boundaries of how we move energy around here in New York City. And I've been working on that ever since.
Was there a particular moment when buildings went from background infrastructure to climate problem for you?
For me, I think it was when I first got the insights into Highmark's operations and how they're working on buildings here in New York City. They were certainly always kind of in the background. 2019 for New York City was really when that came into the foreground as far as business goes. But for me, I had always just been interested in taking things apart, figuring out how things work. When I was a little kid, if a plumber or an HVAC service person came over to the house, I'd be sitting right next to them watching their every move. I was really into robotics in high school. So I've always been fascinated by fixing things and figuring out how things work. Being able to do that with buildings is really fun for me. We're surrounded by buildings and I get to apply that to just about everything I see everywhere I go.
And if we look at a dense city like New York, where you're based, what makes buildings such a hard emissions problem to crack?
There are two main reasons that emissions in buildings in New York City are particularly tough. One is that a lot of these buildings are old.
Mm.
Old buildings are usually very leaky at the building envelope, so they're very drafty, and they usually have very old heating and cooling infrastructure. The common example is, a steam radiator building, right? When people in steam radiator buildings think it's too hot in the wintertime, they don't call down to the boiler room and have them turn their service down. They just open a window, right? And so that kind of old school controls methodology doesn't really fly when you try to electrify buildings. If you were to take that same oil or fuel use and say, okay, give me a heat pump to match that, you're going to get sticker shock and run away from the project. It's going to be much oversized compared to what you actually need. And then the second thing I think is just space. Space is at a premium. New York City real estate is, per square foot, some of the most expensive in the world. And people don't always want to hear that they need to devote a certain number of square footage to HVAC equipment, especially on the roof. A lot of these buildings that are switching over to air source heat pumps, those heat pumps have to go somewhere. And unless you're willing to dedicate a floor or two for a mechanical room on the inside of the building, they're going to go up on the roof. And so when you put heat pumps on the roof, you're gaining electrification, of course, but that's otherwise could be used for amenity space. If it's a hotel building, maybe they could put a bar or an event space up there. If it's residential, they'd love to show off a roof terrace to prospective tenants. And so those are some of the big ones. There, of course, projects in New York City get delayed for all sorts of reasons, and there's plenty of other things to consider. But I think those are the two biggest.
And How old is the building stock in New York? I'm based here in Europe, and building stock here is quite old as well. It depends obviously from city to city, but there have been regulations in place around the kind of insulation you have to put into buildings, the kind of windows you have to put into buildings for quite a while now. What's the situation with that in New York?
The situation in New York varies wildly from neighborhood to neighborhood. You have certain areas where a lot of these buildings are what we call pre-war, and so that's probably 1900s up to 1940s or so. You have other neighborhoods where businesses have exploded and all of those buildings are practically brand new, right? So there are two very different kinds of buildings to try to electrify here in New York. The pre-war buildings can be electrified, but more often than not, doing so would be very costly. And by the end of that process, because you have to redo the facade, you have to redo all of the windows, not to mention making sure that new heat pump equipment going into that building can be supported by such an old building structure. That finished building at the end of an electrification project does not always, remotely resemble that pre-war building at the beginning. And then for new buildings, it's more of a question of what kind of system is going to go into this that we can be future-proofed for. Buildings are a decision that sticks around a lot longer than most other decisions we get to make, right? If you're going to clear a plot of land and say we're going to put a building right here, that's a 100-year decision at minimum,
Mm, yeah,
typically here in New
yeah.
York. It's very rare for a building to go up and 20 years later, the owner of that building decides, we don't want that anymore. We're going to get rid of that. And so you need to make sure that the new buildings going in New York City are not going to run into these same problems that our old buildings are running into 30,
Sure.
40, 50 years down the line.
Right, of course. And in either projects where you are retrofitting and making older buildings more energy efficient, or with newer buildings, designing them that way, what are kind of the things that people consistently underestimate?
People underestimate when they're electrifying these buildings exactly what conditions their equipment is going to be running in. And so this is going to sound paradoxical, but a lot of people will design a heat pump system down to 0 degrees Fahrenheit. And as I mentioned earlier, heat pump systems, air source heat pump systems, there is a drop in performance as you go down to these lower temperatures, below 30 degrees Fahrenheit and then between 10 and 20 degrees Fahrenheit. There is a not insignificant derate, the amount of heat that these machines can put into your building. And so we'll see people say, okay, well, to meet the load of this building at 0 degrees, I need 15 heat pumps. The flip side of that is that at 30 degrees, you probably only need 10. And so people will say, well, my boiler's good down to negative, whatever. It doesn't care what the temperature is outside. And it's in the building codes below a certain temperature, you need to provide heat in the building here in New York City. And so people will say, oh, I've got to electrify my building. We're going to make it all electric. We want it to be as efficient as possible. We want to use heat pumps. And they'll say, we're going to be good down to 0 degrees. We're going to use 15 of these heat pumps. You can operate a building like that, and you might not even get down to 0 degrees, over the course of a winter. We've gone through the hourly weather data for buildings here in New York City. It's something like less than 3% that you're actually spending at 0 degrees. It gets cold in New York City, but the amount of time you're actually spending at 0 degrees versus, the 8,760 hours in a year, it's a very small sliver. And so what we've been trying to bring people up to speed on is don't size for 0 degrees. Don't size for 5 or 10 degrees. Size for 20 degrees, right? Size for 30 degrees. And for those 3 days out of the year where you're below 20 degrees Fahrenheit in New York City, we can use an electric resistive heater in the airstream. We can use an electric water heater that would collect that water in a tank and heat it up with a resistive heater instead of using an air source heat pump. People will think, oh, that seems really inefficient, right? For every 1 unit of energy I put into a heat pump, I can get 2 or 3 units of heat out of it. So
Mhm.
why do I want to switch to, a toaster coil? That doesn't seem very efficient. It's about shifting that strategy for certain temperatures and certain conditions throughout the year. You can be a very, very efficient building and still run inefficiently at 0 degrees or 10 degrees, but you're only there for a handful of hours out of the year. And so by shifting that goal of full heat pump down to 0 degrees to, using heat pumps down to 20 degrees, we can knock sometimes a third of the heat pumps off of that project. And so that's not only less roof space that you have to dedicate to that, but that's less upfront cost,
Sure.
right? It's less scope for the installing contractors to put in there. And that way, you don't have to build a building and say, I installed 15 of these things, and four of them never even turned on last year, right? So it's all about thinking about where the energy is going and not just throwing tools at the job, but figuring out which tool is best for this and how do you effectively use that over the entire year and not just look at the worst case scenario.
Yeah, it strikes me it's analogous to having peaker power plants in a grid that only come on 3, 4 days a year, wildly inefficient generation, but it means that you can keep the grid going even when there's massive demand and you don't have to build out for that full demand. You just bring these things online at point times, similar to your idea with the resistive heating.
Exactly, yeah. And with peaker power plants, you don't have to put them on top of the building, right? You could put a peaker plant 2 or 3 counties away where you have the space to do that. When we're looking at HVAC systems, just about everything we look at has to go inside that building or on top of that building. And so space is really at a premium there.
And just to clarify for my own knowledge, I guess, you're talking about air source heat pumps as opposed to ground source heat pumps. And I'm assuming that's because these are very tall buildings and there's a lot more roof space available to get in air than there is ground space under the building that you have access to.
Yes, the ground space here in New York City, especially in Manhattan, is notoriously crowded. I've walked past construction projects where they've opened up the street and it's pipe spaghetti down there. You have between the internet lines, the phone lines, the Con Edison steam lines, the electricity lines, the sewer, and then you have the subway mixed into all of that. It is packed underneath these city streets. There have been some projects here in New York City that have been able to excel using geothermal technology. Those projects typically happen kind of more on the outskirts, right? So the lower parts of Brooklyn, parts of Queens, the Bronx, as you're getting further away from Manhattan, which is the core of the city. The land is a lot easier to access. These buildings are able to breathe a little bit more. They're not stacked on top of each other. But in Manhattan, geothermal has certainly been a little trickier. That's not to knock geothermal technology. A lot of the technologies that we work with play very well in the sandbox with geothermal. And at the end of the day, that's going to be better than fossil fuels. So, not to knock geothermal there, but in a very dense high rise environment, it's usually trickier to do geothermal.
And where do heat pumps still struggle in commercial buildings?
I think the issue is not specifically with heat pumps themselves, but with the hydronic distribution system you would typically use a heat pump with. Lots of buildings that we're looking to retrofit are usually on steam radiators. Those steam radiators are very different from heat pump systems. The first one being you only need one pipe to each radiator.
Hmm.
If you're using a heat pump system, of course, you could have a packaged heat pump or what we might call a dedicated outdoor air system or a DOAS. That is going to be a machine that takes outside air, will potentially recover some energy with the indoor air that I think we might talk about a bit later, and then push that air into the space, right? So that's a heat pump. It's a box with some fans, and it does the same thing maybe a window air conditioner would, but at a commercial scale. When we talk about heat pumps for heating and cooling every single apartment in a building or multiple office floors of a building. Those are typically going to be air source heat pumps that are pulling heat out of the air and then pushing that heat into a circuit of water. And
Mhm.
so there are pipes carrying this water. That water will go to either fan coil boxes or maybe some radiant heating panels, or maybe to other heat pumps that are in the space and then pump heat from that water into the air, the indoor air. The big difference there is that you now need two pipes instead of one. With steam, you can send one pipe up to your radiator. The steam, as a gas, will rise up. It will hit the radiator, it condenses, and then it comes back to that same pipe and it drops down. And so the cycle repeats, and that's how we distribute steam throughout buildings. You need to use two pipes for a supply and a return when you're on a hydronic heating system. And so the retrofit implications of that are kind of a pain sometimes. When you try to take out a steam radiator, you can't just screw onto that same pipe right there. You need to put a second pipe next to it. And anytime you're, putting new risers in buildings, that's bringing tenants out of the space, it's knocking holes in the ceiling and the floor. And so the biggest struggle with heat pumps, I think now that I've had a chance to discuss this a little bit, is just picking the right kind of system. When you have a boiler, your decision is how big of a boiler and how big of a radiator, right? When you decide you're going to switch over to a heat pump system, now you have to think about you have three or four different options for the terminal units that are actually going to deliver that heat to the space. You have a bunch of different options for how are we going to pump that water around the building? Are we going to use ground source or air source? How are we going to do domestic hot water? Are we going to do domestic hot water totally separate on its own system, or are we going to have one big thermal loop to the building and then pull heat out of that loop to make water as needed? All of these combined with the different space implications of those terminal units means you just have a lot more options to choose from. And that can be good, but that can also make things a little bit more difficult for people.
And you talked about the heat in the subway and how hot it gets down there. What's your view on heat recovery, wastewater energy you mentioned on the intro call, and as I mentioned, the subway heat as part of a decarbonisation toolkit?
Yeah, the subway heat recovery scheme is something that I've been really trying to push here in New York City. And so that combined with the wastewater energy transfer technology and some of the technology that's already in these buildings, energy recovery ventilators are very common. It all speaks to this shifting mindset in buildings today that heat used to be a means to an end and it's now a resource,
Hmm.
right? If you had to heat up an apartment building, you would say, well, I need to put heat into this steam pipe, and then that steam will distribute to the rest of the apartment buildings. And as long as I'm putting enough heat in there, I'm good. Or in the case of air conditioning, we would use chillers to make cold water. That cold water cools down the building. And then we need to get the heat out of that cold water once it picks it up. So we would use a cooling tower. And that cooling tower is what creates all those big plumes of what looks like steam on the top of buildings. And so those are just pushing heat out into the ambient air. When you try to electrify a building, you need to look at where is this thermal energy in the building and what am I doing with it? And so what you'll find is that the old way of doing things was very inefficient because we're not really caring about where that energy is going. We're just making sure that we hit the right temperature here, right? This apartment building needs to be at a minimum 65 degrees, or we need to make sure that we're supplying at maximum 55-degree chilled water. When you start looking at energy recovery, you say, wait a second, all of this heat that we would normally just be spitting out of this building because we don't want it anymore, that's dollars and cents right there.
Hmm.
And so if you can tap into that you would otherwise be throwing away, that has some serious implications, not only on the efficiency of the building, but the cost to operate and also the size of this mechanical system. There are instances where you can almost cut the size of a heat pump installation down by a third or even in half if you just take advantage of the heat that's already in the building instead of pushing the building in two directions at once, so to speak. And so by reframing thermal energy as a resource and not just a means to an end, we can look at ways to recover this thermal energy. That thermal energy could be in the subways, right? The subway trains are powered by electricity, they have regenerative braking, and the subway cars themselves also have air conditioning units inside of them.
Mhm.
So you're getting the friction of the wheels, you're getting the thermal energy coming off of all that electrical gear, and you're also cooling down the inside of the subway cars by making the outside of the subway cars warmer. And so all of that kind of builds up and collects in these subway tunnels. And during the hot summer months, it's possible for these tunnels to reach over 100 degrees. That's one example of like right now, we're not really doing anything with that heat. It's just collecting in the subways, but we could be using it. The MTA could be maybe selling that to nearby buildings through a power purchase agreement. In the example of wastewater, you use however many dollars to heat up a gallon of water for your shower. You take that shower and run your sink, and those dollars are getting flushed down the drain. You never see them again.
Mm.
And so we can put a heat exchanger at the end of your building before that water goes out to the municipal sewer and pull some of that heat back. We can actually recover up to 90% of that heat. And so that's not just cutting your domestic hot water production energy in half. That's dropping it down to 10%. And so now instead of heating up all this water for the next day, you're just topping up that system because we're creating a closed loop for that thermal energy.
Why aren't systems like that more common?
Systems like this are not as common as I'd like them to be for a few reasons. On the topic of subways, it's difficult. It is really hard to convince the MTA that they should be essentially acting as a utility company.
Mm.
That's not the usual book of business. And it's also very hard to go to a big building in New York City and say, oh, the MTA hasn't like technically agreed to do this yet, but I think if we bend their ear, we might be able to do something with your building here. That's simply too uncertain for most building owners to say, yeah, okay, I'll lean on that. In the case of wastewater energy transfer, it's still kind of a new technology, right? The first building in New York City to use wastewater energy transfer came online halfway through 2025. This technology has been used in, say Vancouver for nearly a decade at this point. But here in New York City, it's very new. And when you go to somebody and they say, oh, we're going to put a big heat exchanger that's going to take all of your building's wastewater, they're thinking, well, that heat exchanger is going to clog and I don't want to be the guy to clean it out. It's certainly a new way of thinking about these things, but we've seen new technologies come and pass before, and I'm sure we'll see that again. I would be very surprised if in 10 years wastewater energy transfer was not very common, especially in geothermal applications, applications where you're not in a very dense city core. If you do have some space, like a field or a parking lot or anything like that near that building, that's for buildings with any high domestic hot water demand. So right now we're looking at multifamily buildings, but hospitals have a massive hot water demand because every single patient room needs to have a sink with hot water. Before a doctor does anything, they're going to wash their hands with hot water. That combined with if they have a laundry facility on site, if they have a large cafeteria kitchen on site, all of these thermal loads really add up. And so if we can recycle the heat in that wastewater, that's huge carbon savings, that's huge energy savings, that's huge operational savings because they're using less fuel or less electricity. It's just new. It's in the process of taking off, and I can't wait to see where the industry goes with it.
And how much of this is down then to the likes of regulations? Because again, on the intro call, you mentioned New York's new local law 97 and how that's changing real world decisions in buildings. So, where do you see that kind of balance between the economics, the intrusion that these projects cause and the disruption, and then the regulations coming along and requiring people to make these kind of changes?
Hmm. Absolutely. About a decade before Local Law 97 was passed in 2019, we had Local Law 84. And Local Law 84 said buildings over 25,000 square feet, you need to keep a tally of how much energy you use, how much water you use, how much electricity, how much district steam, how much photovoltaic electricity you can generate on site. All of these different numbers of how much energy and how much resources are flowing into this building. And you need to report that at the end of every year. So that was the first step, was benchmarking, was figuring out where are these buildings right now. Local Law 97, passed in
Mm.
2019, essentially placed greenhouse gas emissions caps per square foot of building. There are different zonings here in New York City, and so each of those different zonings gets a multiplier. So residential, multifamily residential buildings, more energy intensive than, say, an office building or a retail space. And so they're going to get a higher multiplier. So you take all those floor spaces, you add them by all these multipliers, you tally them all up, and so that gives you essentially a limit on how many tons of CO2 that building is allowed to emit. When I say tons of CO2, that's across all kinds of energy, which sounds a little bit complicated, but that just means that the law is looking at the energy grid. It's looking at how often are these peaker plants firing versus relying on renewables. It's looking at steam generation. So when Con Edison uses natural gas to create steam, which then
Mhm.
spins turbines to generate electricity before they send the steam out to the network, they're looking at how much carbon emissions is that steam generation making. And so there's about 6 different types of fuel oil that most old school boilers would use. And then, of course, there's looking at the electricity use by the systems in the building. And so they take all of those numbers. If they're not in tons of CO2, there's an equivalency that's applied there. And then they say, okay, from 2025 to 2030, if you go over this cap, your building's going to get fined per ton of CO2. That cap steps down every 5 years until we reach our goal of an 80% reduction by 2050 as compared to 2005 levels. So 80 by 50 is the big goal for New York City here. And so we had to benchmark, and then we had to put the fines in place. And now we're in that first 5 year stepping stone, and we get to see how the market's responding to that. Local Law 97, when it was passed, was one of the nation's most ambitious climate plans. And so it's really important because this applies to over 60% of the buildings here in New York City. This is 2/3 of the floor space here in New York City. This is over 50,000 buildings. It's basically a coin flip. When you walk past a building, you can flip a coin, and that building is either Local Law 97 covered or not. And so this is really important because 70% of the emissions here in New York City come from buildings. We think of emissions as coming from cars or trucks or maybe the power plants, but those power plants are supplying energy to these buildings. And so
Yeah.
when we look at where all this energy is going, buildings actually have one of the largest impacts on greenhouse gas emissions of anything here in New York City, right? You'd have thought it was cars idling in the street, but it's buildings. And so pushing these buildings to reduce their greenhouse gas emissions means that to get there, they need to reduce their energy use. And so people have been switching to heat pumps as an option.
And are you seeing the results of that come to the fore? I know it's early yet, but are you seeing changes happening as a consequence of Local Law 97?
Absolutely, we are. Highmark was founded in 2012, and they were right on the cutting edge of heat pumps there. Local Law 97, which is in all its complexity, to put it simply, is saying you need to use heat pumps because resistive heating with a 90 something percent efficiency, you're never going to get there. So it's you need to move from old steam powered chillers or fuel powered boilers to heat pumps. The heat pump market has really taken off in New York City since 2019. So we've absolutely seen the market respond to it. There are a couple questions of, are people responding too early or too late? Early, always a good thing. I don't think you really can be too early here. But there are lots of buildings that are trying to kick that can down the road. And a lot of these buildings are maybe co-ops, right? Where that co-op board is not full of engineers and sustainability consultants. They're people that live in a building, or they're smaller multifamily buildings. For the large office buildings and the much larger apartment developments, we have seen them responding to Local Law 97, but it then becomes a question of, are they doing whatever it takes to get into compliance for the next couple of years, Or are they saying, we don't want to have to do another project every 5 years, so let's do a big one right now? So there's a spectrum of responses, but you don't have an option not to respond.
And are the biggest wins then emissions, costs, resilience, or all of the above?
The biggest wins are going to be emissions, but that doesn't discount cost, especially looking at energy recovery, which is enabled by using these kinds of heat pump systems. We're finding that people get sticker shock when they see the upfront cost of heat pumps going into buildings, but when they look at the operating costs, either modeled or when they do measurement and verification in the building after the fact, they are typically cheaper to operate than if you were just to use boilers or Con Edison steam. Resiliency is another big one. It is usually more resiliency in the case that you used to have two or three boilers and now you can have a large bank of different heat pumps. The boiler laws, at least for domestic hot water here in New York City, required about a two-thirds redundancy. So if you were putting two boilers into a building, you'd put a third one there just in case one of the two breaks down. By using modular heat pump systems, we're able to add a lot more of this redundancy without additional units or additional cost or needing additional space. So resiliency has certainly been impacted, but I think the two biggest wins here are going to be emissions and cost savings.
And if we look ahead, then 5, 10 years, what gives you the most confidence that buildings can decarbonize fast enough?
Buildings will be able to decarbonize here in New York City because there is no shortage of creative ideas to get us to where we need to go. There are a number of companies, Highmark obviously included, but we aren't the only ones working on heat pump systems for New York City buildings. Some of these operate very differently. Some of them are more pie in the sky ideas, some of them are more direct drop ins that you can do today. But that kind of landscape of all the heat pump work going on here in New York City, combined with the city's drive to actually make these solutions possible, makes me very optimistic for the next decade. NYSERDA, the New York State Energy Research and Development Authority, have been very instrumental in pushing the adoption of heat pumps and electrification. They have multiple funding opportunities. There's the flexible technical assistance program where you can call them and say, I have a building, we need to electrify it. I don't know where to start, and they'll match you up with an engineer that will come out and help you. They have multiple funding opportunities for thermal energy network projects, for large scale decarbonization projects, even heat recovery. At one point in the past year, they were saying if you're doing a project that does heat recovery of any kind, in any way, shape, or form, let us know. We'll try to get you some funding assistance and we'll hopefully be able to spotlight it and show it off to other people. They were hosting heat recovery roundtables here in New York City. And so it's not just NYSERDA. There's Partnership for New York City, which is really pushing to bring new technologies into this space. The mayor's office, they have some sustainability programs that are also aligned with climate justice. So there is a lot of energy here in New York City for people to try out new ideas, push the limits of this technology and really make their buildings as efficient as they can be.
Good. And for city leaders or building owners listening, what's the smartest first step that they can take right now?
The best first step is going to be seriously taking a close look at what the energy demands of a building are and where you're getting that energy from.
Mm,
We recommend a four-step process, which is firstly sealing the building envelope. Anytime the building envelope is not tightly sealed and you have, air moving freely in and out, it's an uphill battle. You're going to be swimming upstream, oversizing systems, spending more money than you need to. So first things first, get the building envelope in check. That can
mm,
be through passive house construction. There's both an international and a US based passive house standard, and really sealing that envelope is core to the passive house process. Beyond that, you're going to look at what energy you can recover inside the building. So that would be energy recovery ventilators. That could be using wastewater. That could be generating domestic hot water with the heat that would otherwise be sent to a cooling tower. So in
mm.
the summer, when you're cooling down the interior space of a building, you can use that heat to make water for sinks and showers. The third step then is going to be looking at on-site generation. Can we get some more capacity through doing geothermal? Can we do solar panels on the roof? And then number four, the very last step is, okay, we've reduced our energy demand. We've used all the energy in the building. We've tried to make more energy in the building. The physicists aren't going to like that one. Number four is bringing in energy from offsite. And so that's going to be connecting to maybe a district steam system, or it could be a thermal energy network. And last case scenario is trucking fossil fuels into the building.
Fair, good, right? Left field question for you, Drew. If you could have any person or character, alive or dead, real or fictional, as a champion for decarbonising buildings, who would it be and why?
There was a TV show I used to watch as a kid called Mythbusters, and it was hosted by Adam Savage and Jamie Hyneman. And Adam Savage, particularly, most of his career was in prop making and set making and things like that. And he always approached everything with this kind of curiosity that I think was kind of really core to the way that I thought about doing things. So I think he would be a great champion for this. The ability to walk around into any building and basically point and go, what's that? How does it work? And how can we make it better? And to be able to have fun while doing it.
Great, fantastic. We're coming towards the end of the podcast now, Drew. Is there any question that I haven't asked that you wish I had, or any aspect of this we haven't touched on that you think it's important for people to think about?
One thing we didn't touch on too much is thermal energy networks. So that's going to be when you're connecting buildings together. The steam system could be thought of as a thermal energy network, but it's not so much a modern thermal energy network. When you think about solar panels, right, you can take electricity from the grid, but if you're making more than you need, you can give back to the grid. And so you can do that with thermal energy as well. So you just need pipes connecting all these buildings. You can push water in and out. And there are multiple different ways of doing this. You could do a dual temperature loop where the temperature of that loop changes on the season. You could do an ambient loop where that loop is always around 55 degrees, and that operates closer to a geothermal system, except instead of pushing and pulling that energy with the ground, you're pushing and pulling that energy with other buildings. And so really there are opportunities here to connect what we call anchor tenants. And so anchor tenants are nodes on that network that have very, very large demands. So think about a data center, right?
Mm.
Data center has a massive cooling demand. They're giving off lots and lots of heat. There's no reason we can't be piping that heat into nearby homes to heat them up as opposed to burning fossil fuels on
Mm.
site. Sewage is another great example of this. In Vancouver, they have what's called the False Creek Neighborhood Energy Utility, and it's centered at a wastewater treatment plant. And all of that wastewater that's coming in from the surrounding neighborhood, they pass it through some heat exchangers, and they're able to deliver heat through around 6 kilometers of piping to thousands and thousands of residents nearby. And so all of that is heat that we already have, right? You don't need to build a new power plant. You don't need to drill a bunch of geothermal wells. We already have the infrastructure in place to be moving all of this around, and it's just that one key piece of equipment to tap into that. So that I think is another thing that's going to be very important. Regulations right now for thermal energy networks are a little bit tricky, but we have been seeing a lot more pilot projects both here in New York City. Vancouver, as I mentioned, is really excelling in that. Boston is another city doing a great job of transitioning from fossil fuels over to these thermal energy networks. And I think that's really going to be something that we see in the near future.
Drew, if people would like to know more about yourself or any of the things we discussed on the podcast today, where would you have me direct them?
So they can visit the Highmark website. That's highmark.co, not .com, because that will take you to the Highmark Health Insurance. We have people call us asking about their prescriptions sometimes. You can also find me on LinkedIn. Just search up my name, Drew Maggio. So DrewMaggio. And then if you're interested in more information about these kinds of processes, the Building Decarbonization Coalition is a US based organization across all 50 states. And so they are working with policymakers, researchers, and they provide these kinds of quarterly and yearly updates to which states have policies in place, which states have goals in place, and an overview of the technology as well. So that's a great place to learn more.
Great. Drew, that's been really interesting. Thanks a million for coming on the podcast today.
Yeah, thank you.